So happy Monday, part 2. Anyone have questions about any of the assignments before we start? No questions is good news. It means everybody is making good progress and without big troubles. I'm glad about that. I think you're all going to be glad to be here today. Because we're going to cover a very exciting topic, or some very exciting topics on FlowViz. But before we jump into the slides, let's do a preview like we did last time. This is a kind of preview of what's to come today. It is on the topic of stream surfaces. So stream surfaces are an extension of stream lines. And rather than curves being everywhere tangent to the vector field, they are surfaces everywhere tangent to the vector field. And this is what they look like. This is a person actually controlling the length of the stream surface, the integration length. That is a big stream surface from a hurricane simulation. And those are the underlying rectangles that make that the surface is composed of. Because we're using surfaces, we can add texture mapping to them, which is not something you can typically do with just lines or curves. And because we can add texture mapping to them, we can vary the transparency of the texture mapping and add little arrow glyphs, for example, that show the downstream direction of the flow. And the user is changing the textures on the stream surface because they can be modified into different kinds of textures, like different kinds of arrows, different transparency settings. So the user is playing with different options to take different texture maps on the stream surface, just to explore the benefits and limitations of each. So you can use solid textures or textures that are perforated with arrow holes. So those are perforated arrow holes that indicate the downstream direction of the flow. And that's a big, complicated stream surface with lots of curvature and a lot of complexity. Right, so that shows like a very complicated interaction of flow with the surface of a sphere. This is the Hurricane Isabel simulation off the coast of the US. And we can recreate evenly spaced streamlines with these particular stream surface algorithm. That's another very complex stream surface. But we can recreate something called timelines with this kind of stream surface algorithm that we're going to talk about today. And timelines are curves, as you can see there. And they're curves that join a series of particles all released into the flow at the same time. That's what a timeline is. And this is what shaded time ribbons look like. So we can form these small time ribbons and release them into the flow and then watch the behavior of the flow. Ribbons are nice because we can add shading to them, which enhances the depth the perception of three-dimensional depth. We can also extend the same algorithm to path surfaces. So these are surfaces that are always constant to the tangent to the flow in the unsteady flow case. And therefore they can self-intersect, which is something that cannot happen with stream surfaces and streamlines. And this video was made by Tony McLaughlin, who was also a former Swansea University student. Very, very talented student. So that's a little preview. And the question is, what are stream surfaces and how do we construct them? So really what we're talking about is stream surface construction, which is a very good follow-up to 1 week ago. So this builds on the streamline integration, by the way, because stream surfaces are composed of streamlines. But before we jump into stream surfaces, we can discuss stream ribbons. So a stream ribbon is a surface with a fixed width, and it's always tangent to the vector field. And the advantage of stream ribbons over streamlines are multifold, but one of them is, pun intended, one of them is that because it's a surface, we can add shading. And shading is nice for the perception of 3D lighting and shading. And it also shows the rotational properties of the flow. So these stream ribbons can twist around, and then they reflect rotation in the flow. And you can see here, they're essentially formed by two streamlines, and then there's a tiling added to the streamlines, or a stream ribbon, a triangle strip between the two streamlines. Triangle strip is added. Here are two streamlines showing the behavior of flow around this geometry, right? And we can see the twisting behavior down here. So the basic idea for stream ribbon construction or generation is to start with a point in 3D and then add a second point in 3D, a fixed distance from the first point. And then those are two seeding points, and then we join them with an edge. We join those with an edge. And then we integrate both of the points, the first one using streamline integration, the normal streamline integration process, and the second one using this normal streamline integration process. So we get the next 2 points along two parallel streamlines. And then we join them with an edge and fill the space with a triangle strip. Thank you very much. But there is a normalization process. So if the streamlines are diverging from one another, the second streamline is brought closer to the first, such that the stream ribbon always has a fixed width. So that's a width normalization process. So the integrate means streamline integration, which is what we talked about 1 week ago. And then this renormalize the distance means keep the distance between the first and second streamline constant. It could diverge, get closer together, or it could spread apart, which is diverging behavior. But more often than not, it is diverging behavior. And so the position has to be narrowed. And then the stream ribbons terminate the same way that streamlines do. Right? If you leave the domain, you terminate. If you intersect yourself, you can terminate a stream ribbon. If it hits a vortex, an area of zero velocity, it can also terminate. Or you can set a predefined maximum length of a stream ribbon and also terminate it. So those are the termination conditions that we talked about earlier today. We also have other objects like stream tubes. So these are stream tubes, but they show, not only do they show the twisting behavior or the rotational properties of the flow, they show convergence and divergence. So that means instead of being a fixed width like the stream ribbon, there's some allowance for divergence. So when the streamlines spread apart, and convergence, meaning when they come closer together. So you can see that there are divergent properties in this stream tube and convergent properties as well. This is airflow, simulated airflow in a room, by the way. And that's like simulated kind of doorways into the room. And that's a simulated air ventilation. So this is kind of a summary that every time you change the objects, the seed changes, the seeding strategy and the seed dimensionality. So we say that a streamline is a one-dimensional curve and that the seeding object is a point, which is zero-dimensional. A stream ribbon we can say is 2.5D, so it's a surface, you could say, of fixed width. And the seeding object is an edge or an edge segment. So 2 points joined by an edge or a 1D line segment. You could say a stream 2 is seeded using, is also a surface, but in this case, the object that's used for seeding is an ellipse or some sort of a round curve that joins itself. And then we are going to move on to stream surfaces, which are surfaces just like stream ribbons, but they're allowed to diverge and converge. That's one of the fundamental differences. They get more difficult if you allow a surface to diverge. It gets more difficult to construct or put together in a nice and smooth way.